So welcome everyone for our episode of IGCSE Maths Live. My name is Devan, and I'm your host for this episode, along with our expert Ivan Zelich.
Hey, thanks, Devan. Sorry, there was a bit of an internet connection issue right there. So yeah, as Devan said, my name is Ivan. For those of you who might have missed the previous few episodes, I was a master's student at Cambridge University doing just graduated this year. And today we're going to be looking at Algebra Graphs 4. And so we'll get right into it. So we'll be starting with a few key concepts, and the key concepts in this case are speed time graphs, distant time graphs, things like that, and properties of functions. And yeah, there's not too many key concepts, but these are important things to know, and especially for your future education and careers. So let's go into the deep dive. Okay, so distance time graphs. So these guys are very common, obviously, and one key point to look when you're looking at distant time graphs is the gradient, because distance over time is speed or velocity. So when we're asked to analyze them, so obviously a steeper gradient like this means that you're going quicker, and obviously not a steep gradient means you're going slower. And when it's a line like this, the gradient is obviously constant. That's the definition of a line. Y equals mx plus c. M's the gradient. So these guys will be constant m's. When the graph is when the graph is horizontal like this, you're getting the y at a fixed point, right? So that means that it's not moving, it's stationary. And then when you're going down, you're returning to the start. And this would be important for velocity. So I would say the speeds of these guys are the same, but the velocity in this case is negative this guy because you're going the opposite direction. But in this case, these actually guys have the same speed regardless, but they're just in either direction. So in one sense, when we're asking for speed, we're looking at the magnitude of the gradient rather than sign issues there. Okay. There's also these types of graphs. Now, this could easily look like an x squared graph. And so, we did in Algebra 2, we did like derivatives. And so really what the speed is a derivative at, say, at this point. Let's see if I can draw it. So if I want to find what the speed is here, I'll do like a little tangent line here, and this would be my instantaneous speed. Sorry, it's a bad line, but what I mean to do is the tangent. And so, here, as we can see at this point here, the tangent line is a steeper kind of gradient, right? So here it's there, and then it's getting steeper. So from this we conclude that it's getting faster. And yeah, so this is kind of one way to analyze that, and that's kind of the best way to look at it, in my opinion. So yeah, anything else I should add there, Devan, or should we move on?
Yeah, let's move on.
Let's move on. Oh, yeah. Great. So now we have a different kind of graph that often appears, which is velocity or speed time graphs. And I guess here is where we're really talking about negative and positive kind of things, because it's important to negative acceleration. That obviously means that you're deaccelerating, and therefore your velocity is decreasing or your speed's decreasing, and so it's important to know that for sure. Okay, so on the x-axis here we have time as usual. On the y-axis here we have velocity or speed. And so obviously it's showing this graph how fast the object is moving at a particular point in time. So here it's 2 meters per second. Here, meters per second. Here it's 3 meters. So yeah, when you get a graph, always make sure the units are what you're doing. So if it's kilometers per hour, obviously you have to use that in your calculations. Now the gradient of this line is going to be velocity on time, and so that's acceleration. And so, as I said, a positive acceleration would mean that the velocity is increasing, which it is here, and negative acceleration would mean that the velocity is decreasing, and a zero acceleration, which is what in some cases you do assume when you're dealing with quite a few problems, would then be like that. It would just be stationary. And so the velocity is constant at this point, and you're moving at constant velocity. Now, one interesting point which we couldn't really do with, it could maybe still tell you something if you want to know it, but in this case, area under the graph, so this kind of area we're looking at here, actually tells you the distance. So to calculate this area, you could calculate the area of this little triangle, and this rectangle right there, and this little triangle here. And if you did that, you would actually have the distance, the total distance traveled, which is pretty cool. So yeah, you could calculate those that thing and also get that. And yeah, that's really all there is to these kind of graphs. Just make sure that, like in the previous graph where we looked at the gradients, you're accelerating faster if your gradient is steeper, and you're accelerating slower if your gradient is not as steep. And if the gradient is negative, you're deaccelerating. So you're becoming slower over time. Anything else, Devan, I should say?
Just a small thing. Just a small intuition on why the area gives you the distance is that if you take a look at the y-axis, it's in meters per second in speed, while the x-axis is in seconds. Area is basically saying that you should multiply the height and the base. But the height is in meters per second, and the base is in seconds. So when you multiply meters per second by second, you just get the meter, which is distance.
Exactly. Perfect.
Yeah.
Yeah. And one thing I didn't say, sorry, Devon, which was to calculate the area of this guy, you go AB on 2, not just AB, the triangle. So yeah, remember those formulas that you would have learned a while ago.
Okay.
Anything else? Move on?
Yep, let's move on.
Okay, cool. So, okay, now we get to kind of, I guess, the main kind of, is this new or is this always in IGCSE?
It's always been there.
Always been there, okay. Cool. So yeah, I guess I would say that these questions are, in some sense, easier marks in the sense that if you understand it, it's pretty straightforward. And that's good. Always, it's important to make sure you get these concepts because they, you can do them pretty quickly and they carry a few marks here and there. So a function is a way of taking an input and kind of getting an output. We've been dealing with them, well, I guess for a while, just they might not have been called functions. So y equals mx plus c, you put x, and you get mx plus c. That's your output, the y. We've also dealt with square numbers, so you chuck in x and you get some sort of x squared plus bx plus c. That's another function. And so these guys are very general, kind of a way of describing any type of function from a set to a set. So let's just, as we said with these, there are some examples. So one way of writing is f of x equals x squared plus 3x plus 2, or you can think about it, which is this input-output kind of method, is x, you input x, and you output this value. So if you put 3, you get 3 squared plus 3x plus 2. And yeah, the x is the input, and it's a placeholder for the values. So yeah, basically what we've just said here is covered there. So I guess it's best to kind of look at 3 examples rather than talk more about that. So let's just move on to, okay, so you have some more properties of functions. So you can compose 2 functions. This is what I was saying here. And so we'll see an example of it. But say I have a map from a set to a set, then I have a map from the middle set to the next set, then I have a map actually from the initial set to the last set. So if this is my kind of set here and then set, and I have we'll put G. Oops, G. And
It's okay.
and this is another set here, and we have F. Well, then what I could do is I could say, okay, what if I do G and then F? And that's what we're really considering. Is this is how you write it. It'll be just right this kind of notation there, and that just symbolizes that you're doing G first and then F. And so here's an example. So F of x is x squared and G of x is 2x plus 1. So if I apply G first, I get 2x plus 1. And then I apply F, I have to square it. So I get 2x plus 1 squared. So this is what it's saying right here. If I did F first, and so you might be wondering how can you do F first here? Well, because the sets are the same kind of domain, but we're not going to talk about domains. This is why you can kind of do F first and then G. So if I apply F, well, what I get is I get x squared, and then I apply 2 times that value plus 1. So 2x squared plus 1. That's kind of how it works. So we'll see more of that later on. Anything else I should add there, Devon, or just wait till...
Yeah, that's it.
Okay. Now, there's also this idea of inverse function. So I think we've kind of done it quite often just without knowing it. When you have a graph and say you want to know the question, when does this graph equal, when does the y value equal 5 or something, then you're actually just really finding the inverse kind of thing. You're then trying to invert what the line is doing. So and so there's a nice kind of geometric way of doing it. So so the general methods of finding it, which we will see in an example, is you replace f of x with y, and then you have to make x the subject, and then you get the new value. It's kind of what we've done all the time, which is rearranging equations and isolating variables on one side. This is the main idea. So there's an interesting way of geometrically of doing it is if you have this graph right here, you can then just flip across the y equals x line and you get the inverse function. And why is that? So I've just put a little explanation right here. So this graph here will be, for every x value, I output an f of x value for the y. So here we have x and f of x. When I flip it, I'm just interchanging the y and x values, so we get f of x and then x. So it might be a bit confusing right here, but you know, I've got x and actually the y value. So we'll say this is y dash and x dash. So to get y dash from x dash, I need to apply f of -1, because the inverse of f of x will just be x. So I guess that's really an important point to note, which I haven't put there, but when you apply the inverse to f of x, you get x. The same thing if you apply f to the inverse of x. So yeah, and I guess we'll see that later on. Anything should I elaborate more?
Yeah, there'll be an example in the question, so yeah, you can just relax. It's okay. And for the f inverse, it's like saying you bring a number there, then you bring it back. That's why you get x again. Basically, what you input, you transfer it somewhere, then you transfer it back. That's why you get the same answer. That's it.
Yeah. And of course, if you start with the inverse, then it's a bit... the way to look at it is that if f has an inverse, then the inverse of f is just f. Like in the same way, the negative of a negative is still a positive.
Yep.
But
so yeah, that's it.
Okay, cool. Let us go on to the problems. So this first problem is not about functions, so we'll just quickly finish it first. So we have the distance between Prague and Vienna is 254 kilometers, which is useful to know because these are both very beautiful cities. The local time in Prague is the same as the local time in Vienna. So this is obviously a key point, but we'll stop and think after that. A train leaves Prague at 15:20, so 3:20 in the afternoon and arrives in Vienna at 19:50, so 7:50 the same day in the afternoon, in the PM, evening. Calculate the average speed of the train. So when you're looking at average speed, usually it just means total distance over total time. So we'll do that. I mean, that's all the information we have anyway. So step one, so we have to stop and think. So average speed is total distance over total time. So we have the total distance, 254. So what then you do is really calculate the total time. Of course, when we're dealing with problem solving, we always need to be careful of units. So we need to make sure we have the right units that we want. And so we have kilometers, so a good unit would be kilometers per hour. And so what we'll do is we'll find the time in hours. Next, we have to do some calculations. So if I was a person in Vienna and the train started at 3:20 my time, right? Although it's 3:20 in Prague, it's the same time in Vienna. So it's 3:20 my time, and then arrives at 9:50 the same day. The time difference is 4 hours and 30 minutes, right? Because he left at 3:20 and actually arrived at 4:30 minutes. So it took 4.5 hours. So yeah, it's 4 hours and 30 minutes is 4 hours and 30 on 60 hours, which is 4.5 hours. Okay, and then now all we got to do is do distance on time. So speed is distance on time is 254 on 4.5. And I've added this extra step here just because I wasn't using a calculator. So it was just easier to just do that, and then you get 56.44 kilometers per hour. You can check that if maybe I did something silly, but that's the way you do it. So yeah, it's pretty straightforward. It's just be careful and obviously if they said the local time was different, say Vienna was actually 1 hour ahead, so that would mean at 3:20 in Prague time, Vienna was actually 4:20, and then you arrive in Vienna at 7:50. So in fact, the hours decreased by 1, and so it's 3.5 instead of 4.5 hours. So these are the things you just got to be a bit careful of. Okay. Anything else, or should we just move on to the functions?
Yeah, let's move on.
Okay. Let's go. So, question 6. We have these 3 functions. So I'll say them as they come. So h of x is 4 to the x. Find h of 4. So in this case, a function is an input, and you get an output. The input here is 4, and the output is 4 to the x. So it's just 4 to the 4, which I've written as 4 times 4 times 4 times 4 if you want. And you can, that's 16 squared, which is 256. So yeah, let us move on. So that one's pretty straightforward. F of g of 1. So as I said, when you're composing functions, you first do g. So what's g of 1? G of 1 is x squared plus 1, which is 2. And then we apply f to 2. So then we get f of x is 3x plus 2. So 3 times 2 plus 2 is 8. It is that simple. Then you don't have to do much working. I mean, it's worth 2 marks. So 2 lines, 2 marks. Makes sense. I guess in this case, it's maybe doesn't correspond exactly to lines. Okay. So if I apply f of x to x, I get 3x plus 2. And then I apply g of x. Now g of x takes an x and outputs an x squared plus 1. So f of x made x 3x plus 2. And then we have to input that in place of x for g of x. So g of 3x plus 2 is 3x plus 2 squared plus 1. And then we explain that using our binomial kind of formula, where you want to do it. So just make sure that you do 3x in brackets squared, so that's 9x squared, plus 2 times 3x times 2, so that's 12x, plus 2 squared is 4, plus 1 is 5. And that's our answer right there. I guess we should move on. The more practice, the better, really, for these types of questions. Okay.
Yeah, let's do it.
So this is another kind of interesting question. It might look like you don't know how to do it if you practice a lot of function questions, and maybe this is kind of new, but if you just write down, what what you have and what you have to do, then it becomes quite straightforward. In fact, it's almost like doing an inverse. So we could have maybe done E first and then D, but this doesn't really matter too much. So recall g of x is x squared plus 1. So we have to find what g of 7 is. G of 7 is 7 squared plus 1 is 50. And then we have f of x equals 50. So we now need to find x. Now f of x is 3x plus 2. So we have 3x plus 2 equals 50. That's what we have to find x now. We then rearrange, take away the 2, divide by the 3, we get 16. Now, as I said, in some sense, you could have done E first because this is essentially what doing the inverse is. You know, we have a y. Now you have to take away the 2, divide by 3, and make x the subject. But we'll actually do that right now. So, to find the inverse, we have y equals 3x plus 2. Of course, y is really f of x, but in the process, we like to put y instead of f of x for this case. Y equals 3x plus 2. And now we have to make x the subject, or we have to just isolate x. So we take away 2, and then divide by 3. Very similar to what we did here, right? We just solved for 50, but in this case, we're solving for any y. And so the function that f of negative 1x is actually a third of x minus 2 on 3. So you really got to put, instead of the y, you put x. But it's sometimes nicer to kind of put the y. Yeah. Did I make myself clear there, Devon, or should I say?
Yeah.
Yeah. Anything else you want to add, or?
And of course, for the final answer, you should swap the x and y's.
Exactly. Yeah.
And after that, you can replace the y with f inverse of x. That's it.
Yeah. Okay. Yeah. Exactly. I should have put that there, but I missed that. But yeah, make sure you do that, because obviously this is asking f of negative 1 is still a function, so you get an input, and then if you suddenly have a third y minus 2 on 3, it's like, well, what's y? You know, it has to be a third x minus 2 on 3. Okay. So I think this is the last question. No, not the last one. So we're getting there. Okay, so the question is, find g of x on f of x plus x, and write your answer as a single fraction in terms of x in simplest form. So we have g of x is x squared plus 1, and f of x is 3x plus 2. So we have as a fraction g of x on f of x plus x is x squared plus 1 on 3x plus 2 plus x. So now what we need to do is, because it asked us for a single fraction, we really need to, like old times, get a common denominator. So what we're going to do is, we're going to multiply our x by 1. But the 1 is actually 3x plus 2 on 3x plus 2. And so this doesn't change our expression, but it will just get us a common denominator. And now x multiplied by 3x plus 2 is 3x squared plus 2x. So when we add them, we get 3x plus 2 on the bottom, and x squared plus 1 plus 3x squared plus 2x. And then we just write it in simplest terms, so 4x squared plus 2x plus 1 on 3x plus 2. And we can't simplify any further. You would expect that maybe you could because of the question, but it turns out you can't. And one way to see that is to try to factor this quadratic polynomial, but that's not a good idea because it's complex. But what I'm saying is, just leave it there if you couldn't find that 3x plus 2 is a factor, which it shouldn't be because you got a 4 here and you got a 3 there, and it would make it a lot trickier than the question's asking for. Anything else you want to elaborate there, Devon, or we good?
Yeah, that's it. That's the furthest you can go to.
Cool. Okay. So I think this is the last question, I believe. So find x when h of negative 1 of x equals 2. Okay, so how do I want to... Yeah, okay. So the simplest way to do it is to know that h composed with h of negative 1 is just x. It doesn't do anything. So we can literally just apply h, and we get x is h of h negative 1x, which is h of 2. Because if we apply h here, we get x, apply h here, we get h of 2. Now, h is 4 to the x, so x equals h of 2, x equals 4 squared equals x 16. So now, obviously, this was quite straightforward, but there is it's an important point to note. As Devan said, when you're applying h, h negative 1 is like undoing it. So we've undid the x, that gives us 2. So we need to get x. That's, I guess, the easiest way of looking at that. Alternatively, as you know, the inverse of h negative 1 is h. So that's why you just got to apply h to 2. And yeah. Is there anything else I should say there, or I think that's enough?
Well, there's nothing really, but unless if you know how logarithms work, then you can also do it that way.
Yeah, true.
So yeah,
Yeah,
that's it. That's it for today's lesson, actually.
great. Yeah, I don't have anything more to say there. So yeah, let's wrap up. So functions, always important to play around with them. They're very basic objects, a way of getting an input to an output, and we've been dealing with them all the time, but we just haven't written it like f of x. And distant time graphs and those kinds of things, always good to do problems with that. And remember your geometry and area stuff, and the derivative stuff can be useful in some sense, to find the gradient if you want to. And yeah, I think that's all.
Yeah, that's it for today. Actually, just wanna have a small shout out to my friends that came to our live today. Should I mention their names? What do
Yeah,
you think, Ivan?
yeah, do
Yeah.
it.
So thanks, Vincent, Jessica, and Steven, and Owen for coming to our live. This is not really important, but thank you.
Yeah, thank you.
So yeah, that's it for today's lesson. Thank you everyone for watching today's episode, and thank you, Ivan, for being with us today. Don't
It's
forget
okay.
to check out our website and join our Discord server. And we'll see you next Wednesday. Yeah, that's it for today.